As the last example to this topic, we would want to discuss how you apply the Rayleigh algorithm to simulate an uniform circular motion. So the principle is exactly the same as the previous. As long as you know what is the equation of motion for the system you want to simulate, then you can just write down the Rayleigh algorithm and implement it. So in this case, we are talking about an system executing an uniform circular motion. Therefore, you need to know how to describe a circular motion. So a circular motion is um, a point sitting on a circle and assume that it has a vector position r, which is constantly changing in time. So the particle's point p has a coordinate of x and y, and in terms of the polar coordinate, the x and y coordinate is expressed in terms of the radius r times constant theta, y is equals to r sine theta. And here we are assuming that the angle of the particles is changing with time uniformly. So the d theta, dt, which define the uniform angular speed, is defined as omega, which is an constant. So it is assumed that the particle is making a circular motion at a constant speed of omega. Therefore, in order to describe uh, a simple system executing a simple uniform circular motion, the variables that needs to be considered are theta, which is closely related to xy coordinate through these two equations. And also you need to describe the uniform angular speed, which is just your theta dot, which is a constant. And at the same time, you need to know what is the equation of motion for the particles. So if you look at the coordinate in polar system, the position vector r is actually given by r cap, where r cap is the vector that is a radius unit vector pointing radially outwards, and also you have an theta cap, which is the unit vector pointing in the directions of increasing theta. That is, if the circular motion is moving in these directions, that means theta is increasing in this. That means the theta is increasing in this direction. Then the theta cap is pointing in directions where the theta is increasing. Okay, so the equation of motions for this turns out to be that the radial accelerations ar, which is defined as dr d2r dt square, is equals to 0, and also the a theta, which is the angular acceleration, which is defined as d2 theta d theta square, is also equals to 0. So to sum up, the equation of motions for the for the object executing uniform motion, you describe its locations of the point P, instead of in terms of x and y, we describe this in terms of r and theta. So we need to write down the equation of motion for these two variables that dictates the positions of the point executing the circular motion. So the equation of motion for these two variables are such that the AR, which is d2r dt square, is equals to 0. A theta, which is a d2 d theta square, is also 0. Okay, so in some special cases where the a theta, if it's not equals to 0, and r theta, sorry, in the case where a theta and ar is not equal to 0, then the motions will not be a uniform circular motion. It will become something else. For example, um, a equation of motion with non-zero AR and A theta would describe, for example, an ellipse instead of a circle. However, for this special case with zero acceleration along the R and theta directions, the equation of motion is just simply equals to zero. Therefore, we can then simply write down the equations, write down the code for a Rayleigh algorithm that describes the circular motion. As in the previous case, for any circular motions, you need to provide the initial conditions. So how many initial conditions are there? There are initial conditions for R and theta, as well as R dot and theta dot. Okay, so you assume that the particles is making a circular motion with an angular velocity omega, which has to be provided. Then you assume that at time t0, the angle is, say, for example, lying at 0, and the radius of r at time t0 is equals to, say, the constant of the radius. So here I use r to denote the instantaneous vector positions for any point of P, whereas the R, capital R, is the radius, which is a constant. So here there is a slight distinction between the small letter r and big letter R. Here the small letter r is a variable, turns out to be not changing with time. And the size of the circular motions, the size of the circle, is the values of r. So practically in this particular example, small r and big R are the same thing. Okay. Then you need to write down the theta dot, which is the frequency of the angular motion, the angular frequency, or angular speed. And this is just the omega, as I mentioned earlier on, which is a constant. So it starts with from the initial point. When it starts to rotate, you assume that omega is already been set to be a number constant. So the initial velocity is always the same as the omega for the particles on any location at any time when the point P is making a uniform circular motion. So this is the initial velocity of the angular motion, which is also a constant. And you also have to have an r dot. What is r dot? R dot here refers to the r dt, that is the change of the radius as a function of time. And since a circular motion, the radius does not change with time, therefore this is set to be always zero. Therefore, we have the four initial conditions. Theta at time 0 is 0, theta dot at 0 is omega, and r at the beginning at when t is equals to 0, the values of r is the radius r, and the r dot at any time is always equals to 0. So here we show you a code of how to simulate the circular motion by assuming these initial boundary conditions, this initial condition, and also the equation of motion. And this is a code that is implementing the Rayleigh algorithm for the circular motion. Here I set the radius of the circular motions to be 1 with the angular speed omega set to be a number. Then I have to prepare the dictionary that describe the time, the r, vr, theta, and also theta dot. I think somewhere the theta dot is not appearing, but in principle I should prepare the theta dot and r dot, which is this number that I have mentioned here, theta dot, and also the um, r dot. However, as you would see later on, it is not necessary to declare the theta dot and r dot in this particular case due to reason that should be made clear later on. It turns out that this is not necessary. I mean, it is not necessary to declare the theta dot as well as r dot, is because these two numbers are always and constant and it's not changing. So let's proceed and see how we do that. So first of all, I declare my time of simulation. So how long should I simulate it? The time simulation has to be expressed in terms of the period of the circle. The circle has a period of t, capital T, dependent on the angular speed. So the angular speed is omega, which is also the angular frequency. Um, so once you set omega equals to 10, then the period is already set. Then I would want to simulate the circulation motion for 10 period. That means it was going around for 10 closed complete circle. Then I assume the number of grid point in my time grid, then the delta t is then simply equals to t over nt. So here I'm defining the delta t as total as a capital T divided by nt instead of defining as t last. Okay, so the t last is equal to 10t, but my delta t is not defined based on t last, but based on the period of t, which is equally possible. So what I'm trying to say here is that you can define your delta t to be t last or t last, or can be just simply equals to capital T divided by the numbers of grid points. So once I have defined my t last, then I can define the n last, and n last is just the divisions of the total time of simulation divided by the delta t, and you have to take it as an integer. Then n array is just a list of integer starting from 0 up to the last number of n last. Okay, so n array is then containing the information of the time grid. So here, this is the size of my simulation box. The box size can be easily obtained by knowing that the box has an radius of r, right? So this is r. So on the left, it is minus r. On the right, it is minus r. So the total width is just 2r. So is the y also upstairs is r, downstairs is minus r. Therefore, the length of x left and x right are set to be just minus r and positive r uh, as uh, as the limit. Okay, so now I would begin the for loop for the time. So the time at any instance is given by Tn. So the n runs from 0 up to n last. Then I define first my acceleration for the r. And acceleration for the r, as I mentioned, will always be 0. Okay. Then here is the update equations that updates the values of r in the next instant. R is equal to the R of the previous instance times the rate of R changing multiplied with the delta t plus half of R times delta t squared. And after you have updated the R, you update the AR, acceleration in R, then you update the velocity of R. Here the velocity of R, VR is just the R dot. Then this a theta n refers to the accelerations of the angle. So as I mentioned earlier on as well, the acceleration of the angle a theta and the acceleration in r both are equal to 0 according to the equations of motions for the uniform circular motion. So then you update the theta at the next step is just equals to this line of equation. Theta in n plus 1 is the theta at n plus the theta dot times delta t. And then this is just the acceleration contribution. And the acceleration contribution it just happened to be just equals to 0. So I think this should not be half of theta A. I think it should be half of uh, A theta n. Okay, I think it should be half of A theta n. And here it should be Rn. It should be ARn. Okay, so let me check again. The Valais algorithm, here in the first part here is half of A times delta squared. So the last term should be contributed from half of the acceleration times delta t squared. So I think I have to correct my code here. Okay, so um, this would be half of AR times delta t squared, and then here for the theta case it should be half of A theta n delta t squared. Then again the A theta, whether you update it or not, is always equals to 0. Then once you have done that, we have finished updating the theta, A theta n, and also the theta. So here it is seen that the A theta is not updated. I think the omega is not updated. So here, if I want to, I would have to update the, sorry, I don't think that is a I theta. There's a theta dot, okay, theta dot. Okay, so the theta dot here is not updated. Okay, so likewise, here the R dot is updated. Here I do not update the theta dot. So I should have updated, but as I mentioned earlier on, whether I update this theta dot or not, it doesn't really matter. Let me explain what I meant by that. So let's say if I update it, then the update equation for theta dot in the next instant would just say theta dot at n plus this. Okay, it should be plus with the average of the acceleration. So the acceleration here is a theta at n plus a theta, acceleration of theta at n plus 1. But as I mentioned, right, the a theta, that is accelerations along the tangential direction, is always 0. So this is 0, this is also 0. So you can actually omit this, and then this is the theta dot in the previous state. Then this is the theta dot in the next state. I mean, in the time of n plus 1, this is the theta dot at the time before that. And since there is no contribution from the acceleration, the theta dot will always remain constant. Okay, so therefore, the theta dot, whether you update it or not, is always equals to the same number. It is which just equals to the omega. Okay, so it is not necessary to update the theta dot. That's why I omit this one. However, you ask why in that case I do update the VR. This is r theta r dot. But if you look at this very carefully, the acceleration contributions from the radial part AR is also actually 0. So whether I update this or not, it is not going to change anything. Right? So whether I add in these contributions from the acceleration AR or not, it is not going to contribute anything. So this is the characteristics of the uniform circular motion. That is, there's no change in the accelerations. Also, there's no change in the radial direction velocity. That is the r theta dot. That is the say r dot and theta dot is always equals to 0 for the circular motion. There's no change in the magnitude of r, and this is always equals to omega. Okay, so anyway, my code has the contribution of the AR, which is always 0, and here I don't bother to um, add in the update equations for theta dot, because the theta dot is always equals to the omega. Okay, so here this is the omega. So here I do not use theta dot n, but I use omega instead, by knowing the fact that the theta dot which is equal to omega, will always be constant from one end to the other end. So anyway, this is just the Rayleigh algorithm that updates the values of radius r and theta from one time step to the next time step. Once you have obtained the values of theta and also the values of r, then you have to convert it into the x and y coordinate of the particle p, of the point p. So this is the x and y coordinate that is expressed in terms of r and theta. So here for the Rayleigh algorithm of a circular motion, what you do is that you use the equation of motion to update r and update theta. Once the theta and r has been updated, then you have to translate the r and theta into the coordinate of x and y. So that is how I do my circulation. I do my simulation. So here, this is an example of doing the simulation and exporting in terms of an video. So it takes some time to cook up the video. So this is slightly taking longer time than using the display. So let's wait for a while. So here, after waiting for a few minutes, then my video finally pops up. So this is just to show you that how the circular motion can be simulated based on the Rayleigh algorithm. There are some details in the code that I do not explain it here, but the principle is very similar to what we have already discussed in other lecture previously. So I hope that you can try to figure out the details of the simulations based on the Rayleigh algorithm. So as a conclusion, I have shown you a few examples of how to use Rayleigh algorithm to simulate the motions of particles subjected to a force based on Newton's law. Then here is the first example is the simulation of a one-dimensional harmonic oscillator. We have shown you the simulation of a 2D projectile motion using Rayleigh algorithm. And then finally, I have already shown you how to simulate the circular motions of the uniform circular motion using Rayleigh algorithm. So if you understand this, then it should be possible for you to do the assignment questions. So the assignment question here is a little bit challenging. Assignment question on the spot assignment question 19 is a simulations of an orbit, which is an ecliptic orbit. So here, the simulation should produce a result that looks something like this, which is an elliptical orbit. So the elliptical orbit is a result of the force central, what I call a central force acting on the particles. So here I give you the equations of motion that describes the r and theta variable of an object. So here the equation of motion for the radius r is given by this, whereas the equation of motion for the variable theta is not in terms of a theta, but is in terms of theta dot. So you can consider this theta dot as a equation of motion which is a little bit simpler as compared to a theta. So anyway, the equation of motion for a and r are given as this. Then you should be able to try to implement the Rayleigh algorithm for this problem. So what you need to do is actually try to figure out how you update the positions of r at different time, and then these are the constant given to you. The a and b are the constants given. Epsilon, this e is a number which is a small number given to you, and so are the omega, which is also a constant. So based on this constant given, your job is to try to use the equation of motion for the radius r, update it using Rayleigh algorithm, and then you have to figure out how you update the theta variable. Right? So the theta variable here is not to be updated using Rayleigh algorithm per se, but it could be calculated based on some simple consideration. So you have to figure out how to obtain the theta update values based on this relationship. That is, the theta dot is dependent on the values of r. When r changes, then theta dot change, and this have to translate the theta dot into theta. So you can figure out yourself how to do this by using the Verlet algorithm. Okay, so that's all for this video.